By the way, Taylor, I didn't notice any comments from you on the YouTube videos.
Oh.
And he specifically called you out on some of them.
Oh. Lovely time. I watched it old. I watched lecture 1 and lecture 2. And I actually like those because they're more condensed.
Yeah, I know. There's something to be. Wait a minute. What, you saying I talk too much?
Exactly that.
Oh, jeez, yeah. Yeah, there's something to be said about the summer classes. Sure. Anyway, so last time we had started to talk about the epoxides and just a little bit of the chemistry that's involved with them. We went back and we looked at, or maybe we reminded ourselves of how the SUMO mechanisms worked, right? So if we have a SUMO mechanism and we have these partial positive charges which are hopping back and forth between the two of the carbons involved in that 3-numbered ring, and then the incoming nucleophile hits the most stable positive charge. But then we talked about when we have, under basic conditions, we just have the ring strain to worry about, and so then the incoming nucleophile will just ring open from the less substituted side in more of an SN2 manner is what it is. Got it? So that was kind of the name of the game. What did we say about epoxides over? Why are they useful? Right, where now we have a method of making more carbon-carbon bonds using our Grignards or organolithiums. Right, we can also add different functional groups. If, what page is it? We end up looking at the end of the chapter stuff. So page 592, where it lists out all the end of the chapter stuff there. Right? We have a bunch of different ways that we can start to add functional groups next to each other, right? So we can end up with an alcohol and a nitrile group, right? We can end up with an alcohol and a halogen, right? We can end up with an alcohol and another alcohol, right? So different methods and different ways of bringing together, let's say, other functional groups at the end there is what it is, right? So that's kind of one of the benefits of that. Now, I think I mentioned this, I can't remember now off the top of my head, right? But we said that epoxides are basically a special kind of ether, right? So remember in ethers where you have an oxygen, you have 2 carbons bound to either side of it, right? Now we didn't talk too much about ethers in the first part of the first half of organic chemistry. But we'll come back and we'll talk about it a little bit here and now, right? So ethers are actually very useful functional groups. We see them in quite a few places. And we see them maybe most often in the lab, at least in our solvents. Right? Diethyl ether is a very, very common organic solvent that we see. THF, tetrahydrofuran, is technically a kind of ether, right? We see that in our hydroboration oxidation, right? Our BH3THF, that's one of our reagents that we use there, right? So we have a couple of places where we see ethers. They're very, very good solvents. And by the end of the day, we'll be able to explain why they're good solvents under the right conditions, right? So just like with anything in life, right? There's no one thing that's perfect, right? But we have under certain conditions, we have solvents that are better or worse that can be applied in that case, right? That's all we're saying. Okay, so ethers. Yeah, I guess we'll start there. Okay. All right, you guys ready to think?
Ready I almost were ready to think.
Are you guys ready to think? What? Out of nowhere. Oh my goodness. All right, perfect. Okay, so let's say that we have an excess of alcohol, right? Well, be careful how we interpret that, right? We have an abundance of alcohol. Yeah, I know. Okay. One of those days, right? You don't understand, Dr. H. was making ethers. All right, now, okay. So, for science, all right. Anyway, so let's say we have a excess of any kind of alcohol around, right? So we've got a beaker full of it. We have more than enough than what we need, right? And let's say we take that beaker of alcohol and we just add a couple of drops of sulfuric acid to it, some kind of catalytic amount, okay? Some kind of catalytic amount of sulfuric acid. What's going to happen? So show me what you guys think is going to happen. So hang on to that thought. Okay, see what else we can come up with. You're not wrong. That's going to be part of the problem that we'll talk about, right? But or maybe start working through the mechanism to get there. Yeah. All right. I know. It's a. Bigger. Keep going. What happens next? So you guys are both like, make that. What happens? What can happen? So keep going from here. What happens next? What is this? No, what's the name of it?
Acid.
Yeah, it's an acid, right? So it's an acid of funds. When do you use it? That's true, but always in the first step, right? So go ahead and make an ionic acid in the first step. What do you think?
I was looking to see how it tastes.
A little late night studying.
Maybe.
I don't think so either. Something negative attacking something negative. Right? Be careful, right? Remember, what does a formal charge tell us, right? Hey, take a look, right? Something unusual's going on. All right. Until you guys got this. Right? We got sulfuric acid. Now, first of all, how many times have we seen sulfuric acid used? Everywhere, right? And I think when I first talked to you guys about sulfuric acid and organic chemistry, right? This is literally one of the most, I think it's like the top three, one of the top three most produced like industrial chemicals, right? It's literally used everywhere and for everything. And that's great, right? Because it's really cheap to make. All you do is you burn sulfur and you bubble it through water and you make sulfuric acid, right? Really easy to make. It's cheap. It does pretty much everything you want it to, right? But first and foremost, aside from all that, what is it? It's an acid, right? So remember, if nothing else, 10 years from now, right? You guys are gonna wake up in your mansions in I don't know, where do you guys want to live? Idaho, not as cool. Right? You're gonna wake up in a cold sweat, right? Right? You're gonna say, if you have an acid, make it act first, right? Remember, acids are going to be used in the first step of your organic reactions, right? That's just one of these things that happen, right? If you have an acid, make it act like an acid, yada, 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 that kind of thing, okay? All right. There it is. Any of you guys from Idaho? Oh, good, we can pick up on that, all right? Someone on the line is going to get pissed. I would never send my kids to that school. Out of Idaho. You're sitting there eating potatoes. Anyway, right? What did we do here? We did an acid-base reaction. Wow, shocking, I know. What did we make? A what? A good leaving group. What else? Oh goodness. Right? A good leaving group. Remember what we said about alcohols, right? They stink as leaving groups. So we always have to do something to them to make them behave like a leaving group. Got it? What type of leaving group did we make? What flavor, I guess, is what I always call it, right? All right, it's primary. What can you do with a primary leaving group? You can do SN2s, okay? There should be some reason for them to leave, yeah. What else can you do with SN2s? You can do, what else can you do with primary leaving groups? You can do SN2. What else? Huh? Yeah, you can do E2s. I know, just say it. Like I heard it. Say it. People can judge me. Look, there's 9 other people in this class. If they laugh at you, then I'll join in, okay? No, I'm joking. None of you guys do. It's fine, right? So we can do SN2s and E2s, okay? What can we do in this case? Okay, we could do an SN2. What else could we do in this case? You guys got it? You guys get what I'm saying? We could do both of them, right? Because the question then becomes, and like I said, I don't want to belabor this point here, right? This is more an OChem 1 concept, right? If we can do SN2s and E2s, in your mind, you guys should be rattling off the conditions of what we need to do both of those reactions, right? We need strong bases, we need strong nucleophiles, we need unhindered, blah, 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 right? All this stuff that we talked about last semester, right? Now, what you'll notice in this case is we don't have any of that. Right? So we don't have a preference really so much for which reaction could happen. Do you understand what that means? If we don't really have a preference for SN2 or E2, guess what could happen in this case? Both. Guess what will happen in this case? A mixture of both. Right? Now, of course, there's going to be a slight preference for one of them. Right? It's probably going to prefer the SN2. Right? Does it mean the E2 can't happen? Nope. Right? So we have this, right? Let me just change colors, just for argument's sake. Right? So you could do an SN2 where something like this happens. Right? You could do an E2. Something like this could happen. Right? You guys starting to see the problem? One of the many problems, right? So what's one of the many problems? Well, take a look at this right here, right? So if we go through an E2 route, what do we end up making there?
Same thing you started.
Kind of the same thing I started with, but we end up making an alkene, right? And what is this?
Water.
This whole thing. It's a really strong what? Acid. Got it? Can alkenes react with acids? You bet. So what do you think this would end up doing? Well, it could react with this and it could go on to propagate and make a bunch of different products, right? We'll take a look up at the top there in the blue and the green. What do we notice about the positive charge there? Or what do we know about the oxygen? What has a positive charge? What do we know about oxygen with positive charges? They're good leaving groups, right? So this could go on and do another set of reactions, and yada, 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 yada. Do you guys get the point? So what's the product going to be from this reaction? A mess, okay? Don't worry, Dr. H, I can fix this. I'm going to heat it up, okay? Great. What happens when you heat things up?
Everything moves faster.
Everything goes faster. But what if I would heat this up above 100 degrees Celsius? Then what would happen?
You could stop one of them.
What do you mean I could stop one of them?
Do you prefer E2?
Why would I prefer E2? So let's say I heat this up, greater than 100 degrees Celsius, right? What is this right here?
Water.
Water, right? So part of this reaction is
Water.
water. Got it? So what would happen if I start to heat this up above 100 degrees? The water will boil out. Who cares?
It drives the reaction towards it.
Why does it drive the reaction forward? What's that called? Do you remember? The French name? The Chatelier's principle, right? So if I remove one of these components from the equilibrium, right, I have to redo my equilibrium to establish it again, right? So if I heat this up above 100 degrees Celsius, I can drive off water, and then, right, it might have a preference for the elimination, okay? But it would also still have a preference for the ether formation, right? Everything's going to increase. Yeah?
Doesn't alcohol usually have a lower boiling point than water though?
Sure, yeah. So I mean, it depends on the alcohol that I'm going to pick, right? That's the other end of it, right? Ethanol is a lower boiling point than 100 degrees Celsius, right? So it couldn't do it in this case. Do you guys get the point? So if I want to make an ether, what do I have to do? Not this. Got it? Well, gee, Dr. H, why did you show us this? Thank you for wasting my time, right? Whatever. Okay, keep this stuff in mind. I'll come back and ask you guys, okay? So, in theory, if you pick the right alcohol and you add a little bit of sulfuric acid to it, you could end up making an ether out of it, okay? And in fact, for some ethers with the right acidic conditions and the right temperatures, this is how they make the ethers, okay? Why? Well, it's cheap and easy, right? That's how they choose to produce it industrially. Of course, they'd have to come back and that, deprotonate that and yada, 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 that kind of thing, right? But for us, it's not gonna work. We need a better way to make an ether, okay? All right. So let's think of a better way to make an ether. Okay? Let's say that we'll do this stepwise, I guess. Hmm? I'm not doubting. I'm not doubting. I'm not sure to think about it. I'm not sure I just said. I'm not sure I just said. Be careful. I'm not sure what exactly. I'm not sure what to say. What are hybrids? And what properties do they have? They can, that's true. First and foremost, they are really, really good light. Maybe. I would say in some cases, right? Yeah, here it will, right? Yeah, in this case, that's true, yeah. Yeah, so not incorrect, however, under those conditions, right? So going just to kind of clarify the notes here, I would say, how do I say this? So these are hybrids, right? So first and foremost, what's their first property that we always think of? Correct, which means, and it is a what? Yeah. Aha. One of the first types of reaction, right? Cool. Alrighty, so what is NaH? Sodium dry, right? Remember, an H with a minus charge is anything with a minus charge, any monoatomic ion with a minus charge is an IE, right? So hydride, yada, 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 that kind of thing. So an H with a lone pair and a minus charge. Now we've seen those used quite a bit for reduction so far, right? We've seen them able to reduce carbonyls. We've seen them be able to reduce tosylates. Right? Last semester. But anytime you see an H with a lone pair and a negative charge, the first thing we need to be thinking of is that it's first and foremost a base. And so what's it going to go looking for? The most acidic hydrogen. Got it? Well, hopefully at this point you guys see where the most acidic hydrogen is. Okay? Where is it? On the oxygen. Right? So the first thing that's going to happen is the shocking idea of an acid-base reaction, right? So remember when you see sodium or lithium aluminum hydride, any of that kind of stuff, right? You guys are welcome just to think of it as H minus, right? And so if we follow along with step number 1, got it? Okay. So what? That's part 1. How do we get from part 1 to part 2? What did we do in part 2? We made what kind of bond? So we made a carbon-oxygen bond, right? What carbon did we make that bond to? What flavor of carbon did we make that bond to? Primary, right? So if I make a carbon-oxygen bond to a primary, there had to have been a functional group at that primary carbon before, right? And what's the dominant chemistry that happens at primary carbons? SN2s, which means we would have to have a good leaving group there. Do you guys follow along with that train of thought there? Right? We saw we made a carbon-oxygen bond, right? We saw we made a carbon-oxygen bond here, right? That means there had to have been a functional group there before at that carbon, okay? And we have an O with a minus charge, which are powerful bases and good nucleophiles, right? And we know at primary position, the first thing we should probably think of is SN2s. So what could be our blue question mark, right? Our blue question mark is likely something like this, right? Or if you want to go nuts, you can put an iodide there, right? Don't go too crazy. You guys with me? So this is a Williamson ether synthesis. I would have loved to have been a chemist back in the day. But literally what they did is they did an SN2 reaction. Like, yeah, I got a reaction named after me. Okay. So, and for decades they get to torture students. What a legacy. Man. Every organic class we're going to talk about this reaction. And here we are. Do you guys get the utility of this? Why would this be a preferred method for making ethers? Well, right, the first thing is the first part is acid base. Nothing really unusual going on there. The second part is an SN2. Nothing really unusual going on there, right? Acid base reactions are very fast. With sodium hydride, it's extremely clean, right? You bubble off hydrogen gas, right? So there's not too much you have to worry about in terms of side reactions and stuff like that. Not too much you have to worry about in the second part there either. What's the limitations of this, though? Yeah.
So because you're doing an SN2 reaction.
I guess I should have specified. You guys both kind of. So hang on to the thought, Sophia. There. Taylor, what's up?
Isn't it that like the alkyl halide cannot be sterically hindered?
Aha, right? You guys see the bottleneck here is we're doing an SN2, right? So how do we set up a good SN2, right? Well, we have to make sure we have a primary leaving group and all those kind of things, right? So if we have a sterically encumbered ether that we want to make, what do we have to do? We have to be clever about it, Right? You guys with me on this? Right? So we have to be clever about it. You guys want to be clever? Let's be clever. So see what you guys can come up with real quick. See what you guys can get from one part to the other. Anything, right? So what's the first reaction you need to do that? Put something there, right, to do more chemistry. What reaction has a function? Right? Yeah. Good. So now from there, do the magic transformation, right? Yeah, maybe, right? What are you saying about reaction temperature? Sure, metabolic least you nothing very good. What not gonna be trying to. Just asking, okay. I haven't said you're right or wrong, yet, right? So, perhaps it what we might have to do. Right, you got water in there. So what's happening? Secondary crapping some light, right? So I'm not saying you're wrong. This probably will happen within our lifetime at some point. Now you're doing chemistry on paper, right? So it doesn't really matter. But in reality, right, you pick them up differently if you do that. So, you're not wrong, but it's something to keep in mind when you're. So when I ask you a question on the exam, pick the most efficient way to synthesize something. We usually try to avoid SN1 if we can, right? Who's your first one? That's the reaction. Come on, your entire career depends on this. No pressure. That's it. There you go. Good. So put that into play here. All right. I don't like wearing that. I can't make faces at you guys as I walk around. I can't scare you guys anymore. Maybe you guys like it then. Right? So if we're starting out with an alkane, we have to add a functional group. So we have to do some kind of halogenation. Got it? Radical halogenation, light and heat, are radical mechanisms, which you guys also remember. The gazes are suddenly averted. Oh, yeah, remember that? I was working before I came in. Okay. And then there's a couple of different ways we could get up there, right? Yeah, of course, Dr. We know that stuff too. Right? We could do just a simple hydrolysis, going through an SN1 mechanism. That's fine. We're doing chemistry on paper, no real rush there, right? But this is an SN1 mechanism, right, which are always going to be pretty darn slow. So we might want to take a detour here, right? To do, that's terrible. Right, to do an elimination, right? And then do some kind of oxymercuration, demercuration, right? And we avoid the SN1, we avoid the carbocations, and we can make that there, right? You guys with me on this? Yes? Okay. Keep that in mind while I ask the question. I want you guys to make this ether from that alkane. Got it? So you have an excess of that alkane. I want you to make that ether for me. I'll just talk at you guys while you're thinking here. For all purposes, when I give you guys a problem like this, you guys have infinite beakers of that starting alkane, right? It doesn't mean you just have one giant pot and you have to do it all at once, right? So you could take part of that alkane, do something with it, take another part of that alkane, do something else with it, and then bring them two together at the end, which is what you're going to have to do in this case, okay? said that's all you have to begin with, right? Just a plain boron mineral alkene. How can you make that? Starting from that alkene. So where does this come from? All you have is this. Right? So how do you make that? Here's the right idea, but how can you make that? Be careful here. You got one thing carbon. Yeah, so where does that come from? So remember, what I'm saying is your carbon source here is only that alkene. That boring simple alkene. How could you make that complex looking ether from just that carbon source? Hmm? So you guys got it, right? You said you have to do some kind of SN2 reaction, right, on that alcohol. And you do some kind of SN2 reaction with, right? Here it is. Right? Okay, what I saw is you guys took this guy here that we made, right? And you guys said NaH, right? And then you guys said, I saw someone went crazy with the iodine, right? So we'll do that, right? And you guys said that. You said, yep, that's going to make my product. Good? How do I make this from that? Yep.
So maybe, this is me thinking out loud, it's not actually right, so don't.
Now we're doubly going to judge you. All right, but go ahead.
Maybe part 2 of the end, like the Williamson thing might have to be in 2 parts. So we'll attach, like we'll do one, like really, really like simple, alkyl thing, and then again, do it again. I don't know.
No, you're on the right track there, right? You guys want a hint? You can take, you can go from there to there, right? What's the difficult part here? Ignore that it's iodine or whatever, but what's the difficult part? We have to add a functional group to the less substituted side. Why did I ask you guys that question? Or why am I drawing your attention to that? Let me ask the question a different way. How many reactions do you guys know that adds things to the more substituted side? The answer is all of them, except for what? 2 or 3 that don't. You guys with me on this? Remember, here's part of the challenge when you guys are approaching synthesis and organic chemistry is you guys have a huge box of Legos in front of you, right? That we can do a lot of different transformations with. And that box is just going to get bigger as the semester goes along. So just like when you go to Google and you type in a search, right? If you type in a search for organic chemistry, what are you going to get? 10 trillion websites, right? But if you type in a search for organic chemistry mechanism of Williamson ether synthesis using sodium hydride, what are you going to get? The exact thing that you're looking for, right? What's the difference? The difference is you start to narrow down, right? You start to know exactly what you're starting to look for. You have to start to select towards what you want. And so you look at this and you say, I need to add a functional group to the less substituted side. I need to go and think about my anti-Markovnikov addition, right? So what mechanisms do what reactions do anti-Markovnikov addition? So let's think about it. So just bringing down this alkene from up above, right? At the end of the day, I want to make this, right? add some kind of halide to the less substituted side. Can I do that in one step? Yes, you can. Ooh. Can you do it in more than one step? Yes, you can. Okay? You guys get what I'm saying? This is why these questions, I know you guys don't believe me, right? You're gonna say, that's why you guys should like these questions on exam. You're like, dead. Right? There's multiple right ways. Got it? What's the limit? Well, you know, your imagination, so to speak, right? There's multiple right ways, but there's also plenty of not right ways. So we have to be careful of that. Can you guys do this in one step? Yeah, we can. So if we do something like HBr, right? And peroxides. Okay. I heard that. You guys remember this one? You do? Then why didn't you say it? Oh, you did that. Okay, good. Right? So remember, HBr could do an addition reaction with alkenes, and normally, right? Normally it would add Markovnikov, but when we have the peroxide in there, it goes through a radical mechanism. We end up adding our our halogen to the less substituted side. Is that a useful reaction to know? You bet. Okay, you bet. Okay. Let's do it a different way. The way that I think some of you guys are starting to put together. I'll help you along. You guys do that one for me. You better. I think I harped on this enough the first semester. Please don't make my teaching in vain. Spend hours. You know how long it takes to come up with lame jokes about chemistry? Okay? What rhymes with benzene, right? Geez, I'm going to sit here and I love that stuff. How can we do an anti-Markovnikov addition of an alcohol? I'm just saying, how can we do that stuff? Yeah. What are the reasons to do that? No. Okay. I think we'll look at that separately. Where did you already go? You started. Okay. Don't tell me raise it. Good. Perfect. All right. Our good old friend. Our good old friend, hydroboration oxidation. What other method do we have of adding alcohol to the less substituted side? That's right. Sort of, so an asterisk there. Ooh, that sounds like a good exam question, doesn't it? What other way could we do this, Dr. H? Okay, but at the moment, this is by far the easiest way we have of doing that. Is this an important reaction? Remember. Yeah. Okay. Now then. Now we have an alcohol. Now we start to change it into something else. So to to substitute an alcohol, we have to turn it into a good leaving group. One way we have of doing that is turning it into a tosylate. So how can we do that? All right, so our tosyl chloride, right? Okay, there's our tosyl chloride. Oops, sorry, we don't need another one there. Impurity, fantastic. Good. How can I turn that into an iodide? Just for a little flavor. This one's probably not directly in your notes. I know, making me guys extrapolate new things. So what type of, okay, so first and foremost, right, whenever, this is, if there's one thing, all joking aside, if there's one thing I want you guys to start to do in this class is start to think about what reaction is gonna happen. Not in the sense of, hey, have I seen this before necessarily? But remember, we're approaching this from the what is being shown, right? What do I have and how can I do this transformation, right? So my point is this. When I'm looking at this set here, okay, what information are we given? I start out with a tosylate. What do we know about tosylates? Great leaving groups. The immediate next question I ask is what? You guys already know it. What flavor of leaving group is it, right? Primary. Good leaving group that's primary. What's the first thing that should pop to mind? SN2. Okay, so now I'm going to work under the assumption that I want to do an SN2 reaction. To do an SN2 reaction, what do I have to add into this? A what? A good nucleophile. Now, what specific nucleophile do I need to add in this case? Well, I know I want to do a substitution with what? Iodine. How do I make an iodide a good nucleophile? What charge does it have to have? A minus charge, right? So now you're saying, okay, I need to add I minus to this, but I minus isn't a thing. What do I need with it? It could. Be careful with that, though. So hang on to that thought for just a second. Okay, there you go. Sodium iodide, done. Right? Catching me on this one? Just following through the train of thought there. It's a logic puzzle, right? You guys are collecting all the different bits and pieces of data and then saying, here's what I think it would do. Then at the end you step back and say, would that work? Yep. Okay. Now if you do look this up in the book, you'll probably find something like acetone put along with there, and we can talk a little bit about why that is later, but they do talk about these kind of things in the book. It's a Finkelstein reaction is what it's called, the dorkiest of names. I mean, if there was ever a scientist named, I think Finkelstein is right up there, right? But there it is. Good? So, question real quick. Obvious question with an obvious answer. Which method is better? One step, right? So why in the world would we ever want to know the second step then? What's one of the key themes I'm trying to get you guys to pay attention to this semester? Selectivity, functional group tolerance, right? We'll take a look at what we have in the first step there. In the first step, we have HBr. What does HBr react with? A lot of things. Got it? So if we wanted to do this reaction without using an acid, what would we have to do? Go through the second series there, right? Because we completely avoid any acid. You guys catch why that's important to notice then? Right? So what do I expect you guys to know for organic chemistry? Thank you. That's all I really want. You guys got it though? Do you see where the second semester starts to get tricky? Do you see where I'm going to be a jerk? Who said it? I heard someone go, I don't know. That's my same promise that I said in the first semester. I'm never going to trick you guys. But what will I do? Make sure you guys are paying attention. Right? This stuff's already tricky enough as it is. I got it. I promise. Good? So, if you take a look in the book, at the end of the chapter, they have a series of questions that go something like this, right? So just for example, right, I was drawing the same ether that they had there before. Right? They say, propose a synthesis for this ether. And when you're asked a question like that, right, we need to do what we did here. We need to take a look at the two chunks of this ether, right? We break the two bonds on either side of the oxygen and see which of these we could put together in the right way, right? And there's a couple of examples in the chapter where they walk through what we just did here, starting from a different place, okay? Starting from a different view of it, okay? So go back, take a look in the chapter. They talk to you guys about cutting this apart and putting it together. It's also in chapter 12, I believe, is that one? Hang on just a second, where is it? This is chapter 11. Yeah, chapter 11, excuse me. So also in chapter 11, they walk you guys through some of these steps here, okay? Chapter 11 is going to become more and more and more important as you guys go forward in this chapter, in this class. Okay? I mix in chapter 11 as we go through because it's just chapter 11 is all about synthesis, right? Multi-step stuff. Right? So if you wanted a nice condensed place, go look for it there, though. Okay? Good. Brains full for the day? Yeah. What's up?
What other chapter are we on?
We're in chapter 13. Yeah. Brain full for the day? Okay, cool. So tomorrow we're going to do the raspberry synthesis stuff there, right? So make sure you guys have bring your free labs with you again, read through them to refresh what you're up to. Take a look at the TLC and remind yourself of NMR and IR and all that other stuff that goes into it, okay? I'll see you guys then.